Greetings and welcome to this comprehensive course on machine learning and deep learning utilizing Python, Scikit-Learn, TensorFlow, and Pytorch, complete with practical code examples. My name is Ramon Figueiredo, and I'm thrilled to be your guide through this interactive exploration of machine learning and deep learning through hands-on coding. Regression analysis is a fundamental concept in machine learning, essential for predicting continuous variables. Next, we will explore linear regression, a powerful technique for modeling relationship between variables. So, why regression is so important? Continuous prediction. Regression is used when the outcome is a continuous variable. Understanding relationships. Regression helps understand the relationship between variables. Simple and interpretable. Linear regression, for example, provides a straightforward interpretation of relationships. Here is an example of linear regression using Scikit-Learn. In this code, we import the linear regression class from the Scikit-Learn. Then, a linear regression model is created using the linear regression class. Next, the model is trained on a scaled training data using the fit function. Finally, predictions are made on the scaled test set using the predict function. Now, let's see a TensorFlow code for regression. In this code, we use TensorFlow to define a simple linear regression model. First, the model is compiled with a stochastic gradient descent optimizer and mean square error loss. Then, the training is performed on a scaled training data for 50 epochs. Finally, predictions are made on the scaled test set. Finally, let's take a look on a Pytorch code for regression. In this code, we use Pytorch to define a linear regression model. The mean square error is used as a loss function, and stochastic gradient descent is used for optimization. Training is performed for 50 epochs on the scaled training data. Finally, predictions are made on the scaled test set. In summary, regression is a fundamental tool for predicting continuous variables. We explored linear regression using Scikit-Learn, TensorFlow, and Pytorch. Each library provides a unique approach, allowing us to choose the one that best fits our needs. Now, let's go through different types of regression algorithms, explain each algorithm, and provide Python code examples using Scikit-Learn. We already saw a simple linear regression. Here you can see again an example of linear regression using Scikit-Learn. This is the simplest form of regression, involving two variables, one independent, the predictor, and one dependent, the outcome. The linear regression assumes a linear relationship between the predictor and the outcome. The multiple linear regression in Scikit-Learn, it's an extension of the simple linear regression, involving multiple independent variables. That's why the code is very similar to a simple linear regression. The multiple linear regression predicts the outcome based in a linear combination of multiple predictors. Here, we can see the code example for multiple linear regression using Scikit-Learn. The polynomial regression fits a polynomial function to the data, allowing for more complex relationships. It involves transforming the features into polynomial features. This is the code example for a polynomial regression. The Support Vector Regression utilizes support vector machines for regression tasks. It balances the trade-off between fitting the training data and maintaining a smooth model. This is a code example for a support vector regression. The Decision Tree Regressor utilizes a decision tree for regression tasks. It splits the data into subsets based on features to make predictions. Here we can see a code example for Decision Tree Regressor. Finally, let's take a look at the Random Forest Regression. This algorithm is an ensemble learning method that combines multiple decision trees for regression. It reduces overfitting and improves predictive accuracy. This is a code example for Random Forest Regression. In conclusion, understanding and implementing different regression algorithms is essential for various machine learning tasks. Whether you are dealing with a simple linear relationship or a complex nonlinear patterns, these algorithms provide the tools to make accurate predictions. Let's explore real-world examples and provide code snippets for each type of regression algorithm. For simple linear regression, a real-world example is predicting house prices. This is the code for predicting house prices based on the square footage of a house. An example of multiple linear regression can be predicting car prices. This code shows how to predict car prices based on features like horsepower, fuel efficiency, and model year. The polynomial regression can be used to predict the stock prices based on historical data. This is a code example for polynomial regression. Now, let's see the example of house price prediction by using support vector regression. This is the code example for predicting house prices using support vector regression. Next, let's see how to use decision tree regression to predict air quality. This is a code example of how to predict air quality index based on factors like temperature, humidity, and wind speed. Finally, let's see how Random Forest Regression can be used to predict energy consumption. This is a code example of how to predict energy consumption in a building based on factors like temperature, occupancy, and time of a day. These examples provide an idea of how different regression algorithms can be applied to real-world scenarios. You can customize these features and target variables based on a specific use case. Additionally, experimenting with hyperparameters and fine-tuning can enhance the performance of these different regression models. Let's see what are hyperparameters and fine-tuning. Hyperparameters are external settings for machine learning models, not learning from data. Examples include learning rate, regularization strength, or kernel type. They are crucial for model performance and set by practitioners. Fine-tuning involves adjusting hyperparameters for optimal model performance. This is often done through techniques like grid search or random search. Now, let's summarize the advantages and disadvantages of many regression algorithms. Simple linear regression. Advantages: easy to interpret and implement, computationally efficient, suitable for cases with a single independent variable. Disadvantages: it is sensitive to outliers, and as I said before, it can be used with only a single independent variable. Multiple linear regression. Advantages: can model complex relationships with multiple predictors. More flexible than simple linear regression. Provides insights into the impact of each predictor variable. Disadvantages: sensitive to multicollinearity, which is basically highly correlated predictors, and it requires careful feature selection. Polynomial regression. Advantages: captures nonlinear relationships in data. Again, more flexible than linear regression. Can fit a wide range of functions. Disadvantages: prone to overfitting, especially with high-degree polynomials, and it requires careful selection of polynomial degree. What is overfitting and underfitting? Overfitting is when the model learns training data too precisely, causing poor performance on new data. On the other hand, underfitting is when the model is too simple, leading to suboptimal performance overall. In summary, balancing complexity is crucial for effective machine learning. Support Vector Regression. Advantages: effective in high-dimensional spaces. Versatile, can model linear and nonlinear relationships. It is robust to outliers. Disadvantages: the choice of kernel and parameters are crucial for performance. It is sensitive to noise in the data, and it can be computationally intensive for large datasets. Decision Tree Regressor. Advantages: can model complex relationships and interactions. No need for feature scaling. Can handle both numerical and categorical data. Disadvantages: prone to overfitting, especially on small datasets. Lack of smoothness in predictions. Sensitive to small variation in the data. And finally, Random Forest Regression. Advantages: reduce overfitting through ensemble learning. Robust to outliers and noisy. Effective in handling high-dimensional data. Disadvantages: may be computationally expensive. Lack of interpretability compared to individual trees. Awesome! In this part, we learned many regression algorithms. Next, let's delve into classification, where the goal is to categorize data into predefined classes. Let's dive in. Today, I suggest you to dive into real-world code examples using different datasets by actively engaging with code examples on my GitHub repository. This collection covers essential topics that we saw in this video. So, take a moment to explore, test, and tweak these examples. The hands-on experience will empower you to confidently tackle real-world data science and machine learning challenges.